So today we're going to dive into the fascinating world of one of life's most critical molecules, lipids. Now they're way more than just fat. We're talking about the very architects of our cells, the messengers that keep our bodies running, and even our main fuel source. So let's jump right in. Here's the game plan. First, we'll get to the bottom of the one property that defines every single lipid. Then, we're going to play molecular chef and build a fat molecule from the ground up. After that, we'll meet the whole lipid family and see what they do, from building cells to sending signals. And to wrap it all up, we'll see what you've learned. All right, let's kick things off with section 1. What in the world are lipids? Well, the answer starts with something you've probably seen 1,000 times, right in your own kitchen. Yeah, you know what I'm talking about. No matter how much you shake that bottle of salad dressing, the oil and water just don't want to hang out. And that's not just some weird kitchen quirk. It is the single most important clue to understanding the entire world of lipids. The whole secret is in one key word. And that word is hydrophobic. It comes from the Greek hydro for water and phobos for fear. So these molecules are literally water-fearing. See, water molecules act like tiny little magnets, and they love sticking to other molecules that have some kind of charge. Hydrophobic molecules, they don't have that charge, so water just kind of ignores them, pushing them all together. And that brings us to our official definition. A lipid isn't really defined by its shape or its size, but by that one simple property. It's any molecule that's hydrophobic. And this one rule creates this incredibly diverse family. We're talking everything from the fats we eat to the oils we cook with, and even powerful hormones like steroids. Okay, so why is butter a solid and olive oil a liquid? Well, it all comes down to the shape of their molecules. The fatty acids inside fats are perfectly straight, so they can pack together really tightly and form a solid. But the fatty acids in oils, they've got these little kinks or bends in them. And because of those kinks, they can't pack together, so they just flow around as a liquid. Let's take a closer look at what actually causes those kinks. All right, let's move on to our next section, the building blocks of fat. We're going to zoom all the way in and see what these things are actually made of. You see, most fats are built from these long chains called fatty acids, and it's the kind of bond between the carbon atoms that gives them their shape. A saturated fatty acid only has single bonds, which makes the molecule totally straight. But the second you introduce just one double bond, bam, you get a kink in the chain, and now you have a monounsaturated fatty acid. If you have 2 or more double bonds, you get even more kinks, and that's a polyunsaturated fatty acid. So how do our bodies actually put these fatty acids to use? Well, they build one of the most common lipids there is, a triglyceride. You can think of it like a really simple recipe. You start with one glycerol molecule, which is kind of like the backbone. Then you attach 3 fatty acid chains to it. The thing that actually links them all together is a very specific kind of chemical reaction. And that reaction is called a condensation reaction. This is a huge deal in biology. It's like clicking 2 Lego bricks together, and right when they connect, a tiny molecule of water pops out. It's how our bodies build all sorts of huge, complex molecules, including fats. Okay, so we know how lipids are built. Now, let's find out what they actually do. Welcome to Section 3, the lipid family in action. This is where we see how their shape gives them their job in biology. So if we look at the big picture, the lipid family really has 3 superstars. First, you've got triglycerides. That's our main energy storage and our body's insulation. Then there are phospholipids, which are the literal architects of our cells. And finally, you have steroids, which are these powerful messengers, acting as hormones that control, well, just about everything. Now, to really understand phospholipids, we need to learn one more really important term, amphipathic. It sounds complicated, but it just means having both feelings. An amphipathic molecule has one part that's hydrophobic, it hates water, and another part that's hydrophilic, it loves water. And the absolute best example of this is the phospholipid. It is the ultimate two-faced molecule. It's got a phosphate head that is totally hydrophilic. It loves being in water. And then it has 2 fatty acid tails that are completely hydrophobic. They can't stand water. This split personality is its superpower. Because when you toss a bunch of these molecules into water, something absolutely amazing happens, all on its own. The water-loving heads immediately turn to face the water, while all the water-fearing tails scramble to hide from it, pointing towards each other. This spontaneous arrangement creates the phospholipid bilayer, which is the fundamental structure of every single cell membrane on the planet. I mean, how cool is that? And last but not least, let's talk about steroids.
You can always spot a steroid by its signature look, 4 hydrocarbon rings all fused together. And because that ring structure is mostly nonpolar, they are definitely part of the lipid family. This group includes really important hormones like testosterone and estrogen, which act as powerful chemical messengers throughout the body.
Okay, you have taken in a ton of information. So let's switch things up a bit and see what stuck. It's time for a quick recall challenge. You ready? First question for you. If a fatty acid chain is built with only single bonds between its carbon atoms, what do we call that? Saturated. That's right. It's saturated with as many hydrogen atoms as it can hold. And remember, that straight, saturated shape is exactly why things like butter are solid when you leave them on the counter. Okay, next up. What's that special word we use for a molecule that has both a water-loving part and a water-fearing part? Amphipathic, you got it. And that property is literally the reason we have cells. It is the driving force that creates the cell membrane. It's just a perfect example of how the properties of a molecule can create the structures of life. All right, last one for you. This one's a little more specific. When that glycerol backbone hooks up with a fatty acid, what is the exact name of the bond that forms between them? An ester bond, that's the strong covalent link that's created during the condensation reaction, holding the whole triglyceride together. Nicely done. So, as we've seen, lipids are so much more than just a number on a nutrition label. They are the builders of our cells, our main energy savings account, and our body's most critical messengers. When you understand these tiny molecular structures, you start to get a powerful new insight into the huge systems they control, everything from our daily metabolism to our long-term health.